All right, so today we're going to talk about time series models. Remember on Thursday, we were talking about just like the different patterns to look out for it with time series data. Hopefully y'all have seen like at least some of the labs on time series on like how do you deal with time series data, like using all the time series functions within pandas. So today we'll be talking about the modeling where you'll actually like apply the things that you've sort of observed from your time series data. So here is a non-exhaustive list of all the traditional time series models. If you click into this link here, there is a bunch more, and there's like specific syntax and coding examples for each one. So I really like that link for time series. But all we're going to talk about today are, I guess, these. Now, why I say I guess these is because these are all, you can sort of think of it as very modular. If you notice that, you know, there's autoregression in your model, then all of the models with the letter AR, which stands for our autoregression, has an autoregressive component. Here you'll see MA, moving average model, which is another one we'll talk about. All of these models have some moving average component. So it's very additive when you have these time series models. So we'll start simple. We'll start with the autoregressive model, a moving average model. And then I believe our first example that we have is going to use ARIMA. So ARIMA, the I stands for differencing, and I do forget exactly why it's called differencing, but I is called differencing because it's integrated. So you can sort of see that these models all build on top of each other, right? You get from the main ones are like AR, MA. This is both of the first two together. You have differencing, and I would say like the ARIMA model is like a good place to start because ARIMA deals with autoregression, differencing, and moving average, and all of these are add-ons that I will move on to talk about. So when I say that these are additive, they are literally additive. All of these models that we'll be dealing with, very, very similar to linear regression, in which, you know, you have coefficient multiplied by the variable plus coefficient multiplied by the variable. When you add an autoregression term, you're going to have some coefficient multiplied by the AR term and then plus whatever else. So we'll see that these formulas are going to look very, very, very similar to our linear regression model. So just to start, let's start with the autoregressive time series model. So autoregression model makes the assumption that observations at previous time steps are useful to predict the value at the next time step. It's one of the simplest time series models in which we use a linear model to predict the value at the present time using the value at the previous time. So if you can take a look here, we have the time today is equal to some coefficient, and we'll just use phi to represent some coefficient, multiplied by the value yesterday, plus some error term or some constant. So you can sort of think of this as like the intercept term, coefficient, and the variable. So this numeral 1, the -1, I guess, denotes that the next instance is solely dependent on the previous instance. And yeah, the phi is the coefficient that we seek to minimize whatever error function we're using. So the order of AR, and we'll talk about the order of AR, when you hear someone talk about the order of AR, is just a number of lag terms that we're going to use to predict the present value. So if you see AR1 is this formula right here. It's only using one lag. You can also use multiple lag terms. So let's say, you know, you also want to consider part of 2 days before, and we'll see an example later, but if you want to include part of 2 days before, you would see phi2 multiplied by y t minus 2 being added to this formula. So it's literally a linear model. So any questions before we talk about figuring out which one to use?
Yeah, just could you go over what the phi stands for again? What's the coefficient?
Oh, the phi is just coefficient. The coefficient that in a similar way as with linear regression, when you're trying to figure out the best coefficients for your model, this is going to be the best. This is going to be what you're trying to find the best of. So okay. This is an unknown at this point in this formula, but when we run our model, when we get our coefficients out, it'll be the different phi values.
Okay.
Anything else?
So when you say that, okay, it is it's pretty much a linear model. So what if like if within, let's say when we are running any kind of code, first we go through all the linear models and then add on to this?
So not exactly, because it is a linear model, but it doesn't use other features. It's really just using itself. I will talk about one way that you can include exogenous variables. So if you're, because remember in linear model, you're using a lot of x's to predict y, right?
Yeah.
In this case, you're using, there's only y. You're using previous y's to predict current y. You wouldn't use linear regression if you just have, one column of time series data, because you
So
can't.
now, just for my understanding, it will be like, okay, one will be the date column, and the second one will be any of the columns that you want to predict. That's it.
Yes.
Everything else, you're just going to leave it aside, correct?
Yes, to begin with, yes. Yeah. I will say only, you see all of these letters, I mentioned how they were like modular and kind of additive. Anything that has an X, then you can include all of the other variables.
Not clear, but yeah, once we go through it, maybe
Yeah, basically each of these is a different model that we're not going to talk about every single one, but basically like each of the letters in these represent one part of a model. And so if there's an X component, that just means that you can include exogenous variables, which is all the other variables. But anything without an X, which is what we're going to start with, you just have the one column. Like you were saying, you have your date column, but then you also have like whatever values you're trying to predict in the future, whatever you're trying to forecast.
Okay, so let's say there is a stock prediction. So it will say this day the stock closed at this particular time, or like closed at this particular value. Right? Every day there would be the stock value and the date. And it will say that based on this progress which has happened in the past, the future is more likely to be like this.
Yes, yeah, exactly. So those will be up till, honestly, all the models we're going to talk about today, that will be the data that you use.
Okay.
All right, anything else? All right, so how do we determine the order or how many lag terms to include? As you could maybe kind of guess from what we were doing last time, we're going to use the ACF and PACF plots. So why that is, because this is saying that you can use some proportion of yesterday's price to predict today's price. And that just means that this is probably highly correlated with this. If you remember one of our linear regression assumptions, I mean, this is not exactly a linear regression, but the same, very similar assumptions hold. You can probably guess that, for this to be good, you would want this YT minus 1, to be quite correlated or linearly related to Y sub T. But anyways, that's the thought of why using the ACF and PACF curves might be useful. So just a reminder, this is not the exact one, but this is just an example of ACF and PACF. And to start, let's just try out an AR1 model. Now in your labs, you'll see that, actually I can show you here as well, that to use an AR model, you can use like a very specific autoregressive model. Well, because I've said that all the models are additive, I'm actually going to use an ARIMA model. So I'm actually going to use a model that can have differencing and moving average, but I'm going to put those as 0 to begin. But anyways, this will make more sense as I talk about it. So to start, let's take our same shampoo data that we had last time and try and fit a model to this. So I'm just going to do my train test split. One thing to remember is that for time series, the train test split is not going to be random. You usually pick some cutoff point because the whole point of time series is you're going to forecast. So it doesn't make sense to have like random pieces of data here and there. It makes sense when you do your train test split, you're going to choose whatever proportion you want. And then your train will be further back in history and your test will be what you're going to forecast on. So in terms of I guess, terminology to remember. The letters that represent these different terms are P, D, and Q. For almost all traditional time series models, you'll see these letters come up again. So if you actually take a look at the documentation for any time series model, they'll mention PDQ. P is basically how many autoregressive terms you want. D will be how many times you difference your data, and we'll talk about that in a little bit as well. And Q will be how many moving average terms. We'll talk about moving average terms after this as well. But they're always in this order of PDQ. So you can see when I'm fitting my ARIMA model, and this is just me, I'm actually doing this in 2 steps. I can actually, hold on, let me just do it in 1 step so it's not as confusing. There we go. So here, the way that you instantiate it, you actually do instantiate it with your train set as well as the order. Or actually, yeah, it doesn't really matter. We can fit it at the same time. So the order being 1, 0, 0 just means that I want one autoregressive term because I'm doing an AR1 model to start. And I'm not going to care about differencing or moving averages just to start. I'm going to fit the model. You can get the training predictions through the .predict, and then you get future predictions using the forecast. Let me just run this. And just like our linear regression, oh, and this comes from stats models, by the way. This comes from stats models. So just like linear regression, we can get that output that we like to see. So this looks very, very similar. So let's just talk about a few things. So here you can see that as with our linear regression, we have coefficients, which is awesome. We have our coefficient. So this literally says that tomorrow's price will be equal to 231 plus 0.2477 times yesterday's price. Or did I say, yeah, basically 1 day before's price. The sigma is just some overall error, so you don't have to worry about that. But you can also check for your p-values, because this p-value is 0.3. This is actually not a good model to start. Something else, if you remember that in linear regression, we had our R squared. There is no R squared for time series models, but we have AIC and BIC. Now, AIC and BIC are just measures of good fit. Just like how R squared, if you have a high R squared, it could mean overfitting. It doesn't necessarily mean that your model predicts well. So AIC and BIC are also measures of goodness of fit. So definitely be careful with that. And AIC, BIC, the bigger the number, the better, I believe. I always forget which way it is. But the numbers don't necessarily mean anything. So it's always good to have a benchmark and then improve upon that benchmark. Any questions about this so far?
So when we select a benchmark, so do we keep a p-value before we run this test or model?
It honestly, like what you determine to be your baseline or benchmark, it's really up to you. I usually say I like my worst model to be the benchmark or the baseline, just so I can have more significant improvements upon it. But if you want to start calculating, if you want to start your baseline at something with no insignificant p-values, that's fine as well.
Okay.
It just, I guess it also depends on how much modeling you plan to do, like how many different models you plan on testing. But I will say, like, if you're doing an AR1 model, there's not much that you can do to tune it. It's really, you just fit with like one autoregressive term, and these are the results. There are not really any hyperparameters to tune within each ARIMA model if you've already set your PD and Q.
So what happens when we change the 1 to 5?
Yeah, we'll actually take a look at that in a little bit, right after this.
Yeah, so what does that mean, an autoregressive term? What is that again?
Autoregressive term just means that you're going to multiply, you're going to use the value from one time step before. Anything
so you
else?
Could do like 5 days before, like you were saying, or do what? Okay.
Yep, that's right. So we can actually take a look at what our predictions look like. You can see not great if we're just using yesterday's price to predict today's price, you can see because of the general, upswing in the data, this is not really accounted for in an AR model, just because it's using some constant coefficient to multiply by yesterday's price plus some constant. All right, and I mean, just like with linear regression, we can take a look at our mean squared error. You can see that with our, and this is actually RMSE now, within our train data, and you can see our train data actually stopped at 24, so around here. With our training data, there was about 71.2 RMSE, and with our tests, you can obviously see that the error gets greater. It goes up to like 269. So this model doesn't fit super well to begin with, which just means that we only have room to go up. So if you remember let me actually see if I can grab that PACF table that we had before. So from that PACF plot that we had, it did look like that, and this was the same data, it does look like the next two terms would be useful, right? This is the same data. I said that including one lag term for autoregression means that we're using this next day, which is highly correlated, but possibly we also need to include one more. So let's just take a look and see what that does. So next we're going to run an AR2 model. So exactly the same syntax. Instead, we're just changing the AR term from 1 to 2. Do a quick summary. On the one hand, you can see that our p-value for the first one doesn't look super good. This one just goes above 0.05. But now we're using 2 days prior price to predict today's price. So let's just take a look at what the graph looks like. You see, all right, a little better maybe. And with the forecast, you can see that our, let's see, train is 63, test is 257. Let's see if it did better. The train did fit better, and the test 257, 269, marginally better. So it's an overall slightly better model. Let's take a look at these AIC, BIC terms. We have 275 and 279 for our second one. And our first model was 278, 282. So just marginally better. So including more terms, you can see we got a slightly better prediction. We can even try 3, but autoregressive terms are not the only thing that we can add. We can definitely add, we're gonna add a bunch of other things. But before I move on, any questions with autoregressive?
Question.
Mm-hmm.
Oh, yeah, Marvin, you can. He had a, okay, I'll So now when we say orders, is it only related to days, or I mean, if it is week or month, it can be. Let's say if I put 300 days or number 300, so will it only consider as 300 days or how?
Yeah, so if you have AR 300, it's going to consider the price of the past 300 days. This data set only has 36 data points in the train plus test together. But yeah, I mean, if you have like millions of data points, yeah, technically you could have 300 terms. I mean, out of curiosity, let's just see what happens when I put like 5 over here. I mean, you can see there's a lot of insignificance here, but I mean, I don't know if it's going to fit any better. Let's just see the overall results. Well, the error does go down, and you can see that I think it hugs it a little better, but not by much. So we'll see when we come to like the other terms that we can add, how we can make this better. But yeah, technically you can add as many autoregressive terms as you want. Of course, it should be based off of which time lags are highly correlated with what you're trying to forecast.
So if we see the heat map, and within the heat map, if we find, okay, there are certain things which are highly correlated, and if we make those correlated variables as the X,
yeah,
like that we are trying to predict, in that case, like we may not require higher number of days, correct?
Yes, that is true. But just to clarify, we're not going to use a heat map. We're going to use this graph, just because there's no point in like, doing a bunch of time shifts and then doing that big heat map. This gives you all the information. So with this, you could say that, all right, the top 2, maybe the first 2 days, possibly the 16th day is highly correlated as well. I mean, it's in the negative direction, but it's highly correlated. So yeah, I would say don't plot a heat map for time series data because it's gonna, one, take up a lot of space on your screen, and also this graph is more suited for time series analysis.
Okay.
But yes, good instinct on like whichever ones are highly correlated are the ones that you include in your model. Anything else before we move on?
Yeah,
All right.
I actually have
yeah.
a question. So you said that, there's no point in hypertuning, but aren't we hypertuning the, I believe the PDQ every time we adjust that?
Yeah, technically, yes, this is what we're tuning. I'm just saying that like after you have all of these set, there's nothing further that you can tune.
So you couldn't, put this in like a grid search to find which, PDQ values would give you, I guess, like the highest AIC value and BIC value?
Yeah, so yes, PDQ is the only thing that you tune here. What I'm trying to say is past this point, there is no other hyperparameter tuning that you can do past PDQ.
Oh, okay, I see. Yeah.
Yeah,
Okay,
yeah.
sorry.
I think I might have confused some people by saying that, but yes, PDQ are the things that you tune in any ARIMA model. Yeah, but anything else before we move on to moving average terms? All right, so adding moving average terms, the intuition behind that is like sometimes a past value is not a useful indicator of what value will come next, which is what we were dealing with when we included autoregressive terms. So if you consider a system that is subject to a lot of shocks and volatility, that makes sense, right? If you had like, that one day that Bitcoin price went all the way up and then tanked back down again, that wouldn't make sense to have autoregression because then you would predict that the next couple of days are going to be high when that is not the case. So yeah, if a previous time period experienced a shock, it may cause an error for future predictions if we just use that value. A moving average model helps address this behavior. So moving average term in a time series model is a past error multiplied by a coefficient. So this moving average model assumes that present value is related to errors in the past. So it includes memory of past errors. So what we're going to break down here, you can see that this theta, this is the moving, is the coefficient. This term is the error term from the last period. So basically, this model is going to take into account, all right, last period, I predicted something a little bit off. We're going to correct for that change. So I have another resource that talks through exactly how this model is fit.
And what does the mu stand for?
The mu you can sort of think of as like a constant. Just this mu in this particular equation just means everything else in this model. But mu is just, in this case, some constant. Typically in this formula, you don't really have a mu, but this is just used to represent if you have other autoregressive terms, that is what mu is a placeholder for in this instance.
Okay.
Anything else? All right, so if you want to add moving average terms, all you have to do is go into your ARIMA and then address the third thing. So let me go up to the one where at the comments. If you want a moving average term, you would add something to your Q. Before I talk about, before I fit a new model, I'd also want to talk about differencing. So remember differencing from before, any difference value is equal to the present value minus the value at the next lag. What differencing helps you to do is to flatten your data such that moving average terms and autoregressive terms will work better. Because you see here where autoregressive terms failed was in addressing that big increase in your data. If you had difference your data, this would make it easier. And we'll go through an example in a little bit as well. So yep, a time series that needs to be differenced to be made stationary is said to be an integrated time series. And that's where the I comes from in ARIMA. So you can see if at D equals to 0, if there's no differencing, if there's no differencing, that's just that. If there's one difference, then the value for today is going to be today's price, for example, minus yesterday's price. And we talked about this on Thursday. So basically, let's just see what this does. This was our shampoo data. This is at difference once, and this is at difference twice. So you can see that with the difference twice, it overall still becomes flatter. So yeah. So we're going to add two new things at once. The moving average term that's going to take into account prior errors and also differencing. So really quickly, we actually went through this on Thursday. We can just do a really quick DikeFiller test to determine how much differencing is sufficient for our model. So the DikeFiller test, just to refresh, is basically a test for stationarity, which is something that we prefer in our time series data. So just running this test really quickly, we're going to do it on our shampoo values. You can see that, all right, this is it not differenced. When it's not differenced, it has a p-value of 1 of 100%, which is bad. And then the difference data, if we run it again, we run the DikeFiller test this time on the difference data. You can see that our p-value is now really, really small. So that means with one difference, it's differenced enough, it's stationary enough. So for this, as I mentioned before, we're going to use our PACF and ACF to determine how many AR or MA terms. Oh, in terms of MA terms, how do you decide how many MA terms? Typically for autoregressive terms, you look at your partial autocorrelation. But for your moving average terms, you can use your ACF plot. So for your AR terms, PACF. For your MA terms, ACF. Anyways, we're going to run the model, so we'll see. This is a really quick example. Let's just fit like a 2-1-1 model. Basically, that means two autoregressive terms differenced once and one moving average term. So you can see 2-1-1. We're going to do a dot fit. And then this is just me getting the predictions and forecasting it. So really quickly, you can see here, all right, not everything is super great. This moving average term seemed to help a lot. It has a 0 p-value. But how we interpret this is just the same way as we interpret a linear regression. So basically, if I want to predict the price today, the price today is going to be 6.44 minus 0.17 times the lag yesterday, plus 0.21 of the lag of the price 2 days ago, and then just minus 1 of however much the error was from this model last time. Of course, you know, this MA term is not something that you can get straight away. So everything is going to be built in when they make the predictions, because you would have to take into account all the prior errors as well.
Hey, what's the lag again?
The lag is basically which one? So for AR terms, the lag is literally you're going to use the price of however many days before. And then for MA terms, it's going to be the error in your model's predictions from however many time periods before.
So that 6.44, that's today's price, and the lag would be the price of the 6.44 like 2 days ago, I'm assuming?
Not exactly. So 6.44 is just like, think of it as the intercept term. It's just some constant that you're going to add. The price before, you would have to have that information, which is why, you know, when you...
That's the mu. Yeah.
Mm-hmm. Yeah. Okay. Yeah. That's right. So it's hard to manually get these predictions because you would have to look up, all right, what did my model predict prior and prior and prior? So yeah, you would have to start your forecasting from the first time step and then work your way, because you have to deal with all of the error values as well as the actual prices before.
All right, thank you.
You're welcome.
So I have a couple questions.
Yes.
So it says number of observations 23. So basically this is a prediction for the 24th day?
The number of observations being 23, it's because we differenced it once. And so if you remember, when you difference it once, you lose your first observation. And what we're
Okay.
predicting, you can see here, it's a little hard to see, but I fit it on the train set here. And the train set has, well, it started with 24 observations and the differencing was done automatically. And then I'm making predictions on, oh, sorry, this part. I'm forecasting. So the dot forecast method for any of the stats models, time series models, you can forecast however many days in the future.
Oh, so this is 12 days. Well, there were 24 days.
Mm-hmm.
That was our set. Now this is 12 days from that point. It's going to be whatever you add those coefficient AR, whatever that column up.
Ah, okay. So yeah, the forecast 12 means that I'm going to forecast, I want to know the predicted price for the next 12 days. And that's just because when I did my train test split, I had 24 days in my train and 12 days in my test. So this is really just the test, like the test set predictions. Mm-hmm.
Wait, so but it's one number? I'm so confused. It's
yeah. It's a little bit different. Yeah.
So you're predicting, so you're saying this is the test that we're predicting. So we're just seeing if it matches, if it predicted correctly.
Yeah, yeah. Maybe when I have the graph here, let me just plot this out. So when I have this graph here, you can see that, let me just annotate it real quick. Here, okay. So this part is my training data. And then outside this green box, this is all my testing data.
Okay.
You can see here that, you know, the orange line is actually not fitting my blue line very well. That's because when you have like a moving average term or a difference term, it's sort of like working to get it better, if that makes sense. So technically this part doesn't really say anything, but you can see when it's starting to forecast, it hugs the line better. Mm-hmm. Any other questions at this point? All right. So here, so we can take a look at our errors. You can see that our train error is higher. I will say that the train error here is using this line. There is a way to get the, I believe in your lessons, they actually have the correct train RMSE, but you can see the test RMSE is 163 now, which I believe is better than what we had before. Let's see. What we had before was 234. Now we're down to an error of 163. We did see that it is likely that we're going to have more moving average terms. So let's just try that really quickly just to see how that works. So it says around 3, maybe 2 moving average terms. So let's just try 3 just to see what happens. Oops. Oh, what happened here? Thanks. Let's try 2 first. All right. You can see that with 2, the p-values actually did go down. And let's just take a look at this real quick. Yeah. All right, so here we had a test RMSE of 163. Let's just see with one more moving average term. Okay, it went up a little bit. Something that I will tell you all about is with ARIMA modeling, you know, is really just playing around with these 3 numbers, which can get a little bit, you know, what's the word? Cumbersome when dealing with all of these, like these 3 hyperparameters, because sometimes it's not very clear, you know, like for example, with this 3rd term here, like, should I keep this as a moving average term or not? One thing I'm going to share with you all is that there is like a grid search for ARIMA modeling. I think Edward, you sort of like alluded to having that. But, you know, it's always good to have it's always good to have an idea of, you know, what your terms are going to be. Then you can sort of set up a grid search to search through your PD and Q. Using the library that I have here, I've actually linked it down here that does like a walkthrough called Autoregressive. So Autoregressive will basically, you have to set up your grids, of course, and like the range of values you want to search through. But Autoregressive will actually run a bunch of ARIMA models for you and figure out which is the best model for you to use. So yeah, if you take a look at Autoregressive, I'm not going to go super in depth, but I just want to show you what the outputs will look like. So you can see here, I hope you all can see here. Let me zoom in. right, you can see here they are fitting these ARIMA models with like these different PDQ values, and then you can basically see the AIC and BIC scores for this.
Does this just work for ARIMA, or does it work for the other ones too?
It works for ARIMA. It works for everything before ARIMA. You can sort of see here that there's this like multiply part. So this is actually for seasonality that we're actually going to talk about next. So you can include all of these as well.
All right, thank you.
You're welcome. Any questions at this point?
Yes, so are we normalizing everything, like getting with the seasonality, and what did we do that in this model?
So you don't have to scale your data with time series. By normalizing, if you mean differencing, or do you mean just like?
I guess I just mean, well, you didn't want it to have like a big trend line, and you didn't want to have a lot of seasonality in your data, in your time series data. What would be the term for that?
So yeah, the next thing we're going to talk about is including a seasonality coefficient.
Okay.
And then also with the differencing, you actually don't have to difference your data before you feed it into the model. You see here that when I did have this differencing term of 1, I still fed in the same training data because they do the differencing for you when you run the model. Anything else at this point? All right, well, the rest of it is honestly just additive. So the next thing that we add on is exogenous variables. The last thing we'll do is with the S for seasonality. But the next thing we can talk about is exogenous variables, which you can basically extend ARIMA to include additional variables that might have an impact on what we're trying to forecast. So for example, if you want to do, I don't know, like the stock price or like the price of S&P, and you think that it is highly correlated, whether positive or negative, with like the price of gold, for example, you can include that as a variable. And basically you'll see that when you have your output, you'll have a coefficient for the price of gold, just like that. Something that you have to consider when you are, when you want to add variables into your model. First, does your exogenous variable actually impact your endogenous variable and not the other way around, right? I think something that I might have talked about last time was confounding variables. Make sure that all of your X variables or all of your exogenous variables are things that are not a result of what you're trying to predict. So make sure that it's the other way around or they're just happening in parallel. Does that make sense? So for example, if I'm trying to predict the stock price, an exogenous variable should not be what people are saying about today's stock price. You can use what people are saying about yesterday's stock price, but not what people are saying about today's stock price. Questions about that?
Yeah, so what happens when, let's say when we were working on the housing data set, right? There were correlated, like the bedrooms were correlated, right? So there were different things that were correlated highly, and like it just had a strong linear relationship while the prediction happened. So now how many variables here can we add as the extra ones?
Okay, so the thing is, how many okay. Basically, one, you should still get rid of multicollinearity because it's still a linear model. Okay. So you still have to check for multicollinearity within your like other features. Next, you also have to consider if you're trying to predict the price of a house, you have to think about, does it make sense to predict the price of one house using time series? Because that means you would have to have the past price for the same house for however long your period is. Now, what you'll see that the project for time series is you're predicting the average price per zip code you're predicting the average price for a zip code over, I don't know how many, I forget how many years the data set is. So it's more aggregated. So in terms of like, you're not going to get as granular as like the number of bedrooms per house, but you're going to use other features that also exist in like a time series way. Does that make sense?
So like it will just say that, okay, this zip code over the years had, right, the kind of fluctuation which it had. Only based on that zip code, it will give the prediction that what is the next price for the next 10 days, 12 days, whatever number of days that we
Yes.
set there. It will give the prediction on that.
Yes. If you are trying to use like bedrooms and bathrooms to predict the price of a house in time series, you imagine you just so happen to have your market value of your house, maybe like every month for the past 10 years. You just happen to get it, I don't know, what's the word, like valuated? You get your house like appraised? I don't know, I forget the word.
Appraisal.
But basically, yeah, you get your house appraised every single month. So you have that data. And you also keep track of the little changes you're making to your house every month. Then you can use the changes in the features of your house to predict price.
So basically, as long as there's a high correlation between the price and the changes, then you can use the changes to do that. Is that what you're saying?
Yeah, kind of that. Yeah. I wouldn't use the word correlation, but basically the data that you want to use as an exogenous variable has to be collected in the same like manner as what you're trying to forecast.
And you can set the parameters for that manner.
Well, the manner is, yeah, based on the data that you have. So, well, let's say I'm trying to predict the price of my house next, like on a monthly basis for the next few months. The data I have that is collected on like the number of bedrooms, maybe like the square footage of my garden that I manicure has to be collected monthly.
So it's in terms of the time. So the time frequency has to be the same. Then you can like see it as a parallel with the actual price.
Yes, that's right.
All right, cool.
Yeah, let me see if there's an example in this one. I'm actually not sure if they have Sarah Max here. So you can see that here, this is just like a random data set. Let me zoom in, sorry. So this is just an example of using Sarah Max. We haven't talked about the S part, but we will in a little bit. It's actually pretty straightforward as well. But in Sarah Max, you can see that data 1 is the time series data. Data 2 will be your exogenous variables. So here, the way that you fit it, you just give it your data 1, your time, whatever you're trying to forecast, and then you feed it in all the exogenous data. And that's really all you have to do to include exogenous information. You just have to instantiate a different model. Instead of ARIMA, it will be Saramax, but yeah. Any questions about this? All right. Well, the last thing we're going to talk about is, oh, sorry, one more thing to mention about exogenous variables. They also need to be different at the same order as endogenous. So usually if you have an exogenous variable, you want to plot it and just make sure that it has like at least a very similar trend to your whatever you're trying to forecast. And yeah, in this case, it would be a good idea to like take a look at the correlation of your forecasting variable with what you're trying to use to predict it.
So quick question on that. If it wasn't correlated, or let's say, it didn't follow the same trend, then that would be a sign to not use it, correct?
Yeah, because how the exogenous variables come into play, it's just going to be plus coefficient multiplied by the exogenous variable. So if it's not correlated by some coefficient, then it's not likely going to be a useful variable.
All right, thanks.
Anything else before we talk about seasonality? Cool. All right, well, seasonality, again, as you saw here, is pretty straightforward. Wait, let me go back here. You can see that with seasonal order, all you have to do is give it some seasonal order, and your model will account for seasonality in your data. So with seasonality, unfortunately, at least not that I'm aware of, there's no way to test if seasonality actually exists or not. It's really through eyeballing it to see if, all right, are there patterns that persist year over year? So one, you have to determine the periodicity of your data. That doesn't sound right, but determine the periods of your seasons. So for example, do you have like the same peaks and troughs every year? Like, does your stock price peak in March? Does it crash in like October, for example? If that is something that constantly happens, your period is going to be 1 year. And 1 year, then you have to think about, all right, how many data points do I have per year? If it's stock price, usually it's like, I don't know. Well, let's just say 365. Let's just say that you have a price every day. Let's not think about the weekend stuff. If your data is monthly, your seasonality will be 12 because you have 12 periods in a year. That makes sense. So that is a number that you feed in for your seasonality.
So you will just mention it as like 0, 0, 12 times. If it is like, I mean, the one which we have here is based on 4 quarters, correct? Like the day, like you had.
Oh, the shampoo data?
Yeah.
Yeah. So the shampoo data, the shampoo data is monthly. So for example, if there was like let's say in the 2 years of data that I have, let's say every other month it's high, low, high, low, high, low. So then my seasonality, I would put 2 because one round of all the seasons is 2 periods or 2 data points.
Can you just go through that code?
Well, that's not seasonal, but let's see, like, for example, this one. This is airline passenger counts, and this, you can see each one is a year, so you can assume that this is monthly data.
Oh, okay.
Right, and you can see, I mean, you should difference it first, but you sort of see that the low is always right before the new year. Right, so right before the new year is the low, and if this is monthly data, then you put 12 here. This is just however many data points there is in one revolution of your seasons. So then this will be just your PDQs, and then you will just add on your seasonality.
We don't need to change in the numbers on the PDQs, right?
Yeah, no, you don't have to change.
Yeah.
Yeah. The code, honestly, it's the same. I do have a walkthrough. Oh wait, well, this is the documentation that I have linked here, but I also have a walkthrough for Saramax. So you can take a look at this project that someone did that actually, includes exogenous variables and also includes seasonality. So you can take a look at their EDA, how they determined what was the best PD and Q to be, how they determined the best values, and then, feel free to look through this. I think this is a pretty good walkthrough. They had like an overall error of, I don't know, 78, and this is predicting, I think, taxi demands, which is, I think, pretty good. But yeah, I mean, whenever you have seasonality, that's also something that does show up in your coefficients. So yeah. Any questions? That's all I had to share for today, but yeah, any questions to round out?
Could you go over endogenous and exogenous again, what it means?
So endogenous is the variable that you're trying to predict.
Which one again?
So
that is that
basically,
endogenous?
like, endogenous is shampoo, for example.
Okay.
Exogenous
price.
would be like maybe the price of soap or the price of like conditioner.
Okay.
So
you're
yeah,
saying that it does have exogenous variables. You have to determine whether or not they have a correlation.
yes, I mean, it only makes sense to use something to predict the price of shampoo if it's correlated with the price of shampoo.
So sometimes you do want to use exogenous variables and sometimes you don't. You have to determine the correlation.
Yeah, I mean, sometimes you just don't have any data that you can use as exogenous data. So then in that case, there's nothing that you can do. But let's say in this data set, I had shampoo price, I had conditioner price, soap price, dish soap price. I would see which ones are correlated with the price of shampoo, and the correlated ones I would use.
Okay.
Mm-hmm.
So what I understand is now let's say if we have the New York Stock Exchange prices and it is related to, let's say, Singapore Stock Exchange, or let's say any other stock exchanges across the world. So if we are able to determine that, okay, as let's say, as one of the stock exchanges go up, the New York Stock Exchange also goes up for a particular product, whatever product which we have selected. So if we are able to determine this two relationship, then right, we can use that as the exogenous.
Yeah, exactly. Given that, you have to make sure that the direction of causation is correct. So yeah, I mean, just through your example where, like, you know, you brought up the example of like a Singapore stock market, and Singapore is like 12 hours ahead. So their price would come first before America's prices. So yes, it does make sense to use Singapore stock price to predict the New York Stock Exchange price. If it was the other way around, it wouldn't make sense, because you would have like the order in which, you know, you get your data is different. Yeah.
Sorry, so kind of connect to that. So why would it not work? Why would it be problematic or whatever to use, like you said, I think like Twitter things that people were saying about a stock as like a variable in the model?
Right. It's important when it was collected. So if I'm using what people were saying about Tesla stock, Tesla is actually one that's very, very impacted by tweets. If I'm trying to predict Tesla stock using, for example, Elon Musk's tweets, it's hard to predict. You have to use Elon Musk's tweets that come before the time you're trying to predict. Because imagine if I want to predict the price for tomorrow, I don't know what he's going to tweet tomorrow. I have to use what he's tweeting today.
Well, what if you did like tweets that just like mentions how the number of tweets across Twitter, and you can see that from the day before to see how that affects the next day?
Yeah, I mean, it only comes, I mean, it's really like, if you're trying to actually make forecasts, you have to just make sure you're able to get the data that you're using to make the forecast. So that also has to come into play with your training data. The way that you match up your exogenous variables with what you're trying to forecast, just make sure that your exogenous variables, you would be able to get that data before whatever you're trying to forecast.
Right.
Yeah. Cool. Any final questions? All right, well, just so you all know, within the time series, if you do want to do a time series project this time, I'd highly, highly recommend that you do. There's only 2 extra lessons in the appendix section. One of the appendixing is actually a SARIMA. I think it's a SARIMA without exogenous, so it's that. And then the other lesson that's in your appendix is using this model that was built by Facebook. It's called Facebook Profit. It is actually very, very similar to like a Sarimax model, but it does have a little bit of learning, like there is a little bit of machine learning going on behind it. I haven't gotten to look into the math that actually goes behind that model, but it has been shown to predict better than these traditional models. So in your project, you're allowed to use that. Also, if you're thinking of continuing with time series for your capstone, for example, we will be talking about how you can use neural networks on time series data when we get to neural networks. And that will be, I think, the very last study group that we have. So yeah, any final questions to close out? All right, then. If there's nothing else, I will see you all back here on Thursday, and we will get into natural language processing. All right, bye everybody. Have a good night.
Good night.